All right. Well, welcome to day 3 of TechCon 2025. We've had some great sessions, got some more great sessions for you today, and then at the end of the day, another office hour. So glad to have everybody with us, and I'm going to we've got a session here on how to use RAG in event automation, and Joel Hansen out of our development lab is here to take us through it. So without any further ado, Joel, take it away.
Hello, everyone. It's great to be here today at TechCon 2025. My name is Joel Hansen, and I work as a software engineer working under IBM event streams. I'm mainly focusing on the connector side of things in event streams. Today, we are going to explore one of the most exciting areas in AI retrieval augmented generation, or RAG, which is powered by event automation. So, with the rise of large language models, the need for real-time contextual data and trustworthy data has become crucial. That's where the event streaming and the automation comes into play. Throughout this talk, I will cover how we can use event automation to build real-time RAG applications, making AI more accurate and dynamic. I'll walk you through a live demo of an inventory management bot. We will also touch on other real world applications, for example, customer support AI, or a system that detects credit card fraud. So by the end of the session, you will understand why event-driven architecture are the missing piece in AI-powered applications, and how event automation enables this transformation. So let's dive in. We will start off with the understanding of what is RAG, what is event automation, and then go to the technical details, the key components, demo, and the benefits of using this. So take this as an example. So I have a chatbot. So if I ask the chatbot about the availability of XM5 headphones in Chicago store or any store, current chatbots won't be able to figure out what are the available stock, what are the current prices, because it's trained on a previous data that was downloaded and trained upon, and it doesn't have the context, the current context of what is happening with that product, what is the current price and all. So you might have seen a template like I don't have access to the current inventory information. The plain template information would be provided. So it would also provide us where can I find this information. Rather than this, consider a scenario where you would be able to get the current amount of stock within a store, as well as the current price. As well as you can also enable the chatbot to order the items through a chatbot, and provide feedbacks of how much would be the delivery cost, if it's in 2 days, if it's in the next day, and in the same day. So for this, it requires real-time data, like how much does it cost for it to be delivered, how much is the logistic data, like so. With the context, the chatbot would be able to provide a more accurate information, and doesn't provide a template data or a hallucinated information. So with RAG and event automation, AI gains the access to real-time contextual knowledge. This enables accuracy, reduce hallucination, and allow AI to respond in a dynamic manner. So yeah. So why do we need event automation? So as I said, we need real-time data. Right? So we can't collect all the data and train the chatbot all the time if you need latest information. So with event automation and RAG, so RAG comes in the part where we need context, right? So for context, to store the context in somewhere, we use RAG systems. RAG systems is where we store the contextual information. Like let's say in the previous example, the XM5 the availability of XM files, right? So if the inventory management system is able to update the RAG system, saying that we have this much amount of XM files in a particular store, the application could fetch this information from the RAG system, whether it's be in a MongoDB, Melviz, or in Postgres. It can get this information and make the response more interactive with an LLM. Like the response from a RAG system won't be that meaningful if we don't combine it with LLM. So event-driven AI application could provide this fresh data to RAG systems. So these RAG systems require to be ingested with latest data. So event-driven applications could be able to ingest a latest data as and when it arrives. So event automation plays a crucial role, providing streaming, the processing of these events. We can't ingest the same data that we get from a system to a RAG database or a RAG system. So it needs to be processed. That's where event processing comes into play, and also the governance and management system. That is done by the event endpoint management. So the key question is, how do we automate AI responses with real-time relevant data? So we'll start off with what is RAG. So RAG, as you all know, it's a retrieval augmented generation. It's a technique that improves the accuracy and relevance of LLM generated response. It's by providing real-time domain-specific knowledge instead of relying on solely on the static data that it's been trained on. We fetch relevant live data, use it as an additional context during inference. So RAG works in 3 steps. RAG retrieves the relevant documents. The system retrieves relevant documents for passages from a large corpus, like a Wikipedia page, could be split into multiple chunks, and that could likely contain the answer for our relevant information. So we combine the query and the retrieve document that with the original query to provide context for the generative model. So a generative model generates a response based on the combined input of the query and retrieved documents. Let's take this example. What was the significance of Apollo 11 mission? So it first retrieves the documents, like it has the information, like it's the first mission, who was the first person to land or walk on the lunar surface. It was a major milestone. All those relevant documents could be fetched using a RAG system. So we combine the query and retrieve documents. The retrieved, it's a context to provide inputs for a generative model. With combining the document information and the LLM, it's able to make a better response similar to this. So how do we ingest data into a vector store? So we start off with the raw data. It can be documents, it can be articles, it can be JSON messages, it can be FAQs, etc. So it starts off with pre-processing. It pre-processes by cleaning the data, remove unwanted characters, stop words, normal pre-processing stuff where we normalize the data, tokenize the text, remove sensitive data, all those things. Then comes the chunking part. We split the text into multiple smaller chunks, ensures the chunks are seen, it's meaningful, right? And comes the embedding part. Embedding part is where we use an embedding model. We can use watsonx, we can use OpenAI, we can use any open source models that gives us embedding capabilities and converts them into a text chunk which has the numeric representation or vectors for it. So we store this embeddings into a vector store. As I said earlier, it can be Melviz, can be Postgres, can be MongoDB, whatever it is. we store this information, we store these embeddings with the original text into the database. So this is the normal workflow of how the insertion happens. Let's take the document where Apollo 11 was the first mission, and to land humans on moon and the other relevant data. So it's starts with the pre-processing of the data. It cleans, like it normalizes the data, removes stop words, remove unwanted references, all those things. And it starts with chunking. It can be split into 3 chunks. After making them a meaningful chunk, they can be embedded using an embedding model. These embeddings can be stored into a vector store. So while storing into a vector store, you have to provide a reference where this document comes from, as well as the text and the chunk embedding. So as I said earlier, we require event-driven RAG. So this can be done with a batch processing, right? So why do we like with batch processing? As I said earlier, it can't have the latest information. So event-driven RAGs, where whenever a new data comes in, we would process the data, ingest into the vector database. We use the information by the LLM to give a more accurate response. So this is where event-driven architecture comes in. Instead of pulling data from a static source, we continuously stream relevant information, making AI more reactive and intelligent. IBM Event Automation, powered by IBM Event Streams, we could ingest real-time data. Event Streams is the backbone to provide event-driven architecture. This fuels the all AI application. So batch processes as a special case, it can be considered as a special case of stream processing. Core principle behind design of Apache Flink, it was articulated by Fabian and the other guy, that batch processing is a special case of stream processing. So considering that, it would be easy for us to relate to some of those things in Flink. So to make RAG work well, companies need to tackle key challenges that include outdated data, scattered data, poor quality data, and lack of trust in the data. So these are the common challenges that come into play in a system like this. So what is the advantage of using event automation, or why can't we go to a different solution? So as a customer, you could use the same entitlement keys to access the whole event automation profile, which includes event streams, event endpoint management, and event processing. We can also use the IBM watsonx service to use the state-of-the-art models that are available right now. And the whole architecture would be secure and scalable. So consider these are the 3 components. So under the hood, event streams uses Apache Kafka, and event processing uses Apache Flink. So Apache Flink is used for transformation and to act on this data. Apache Kafka is to store the events coming into the whole event automation system. So this would be the technical architecture if you're considering using a RAG with event automation. So we could ingest multiple sources, data from multiple sources using the connectors. Event streams provide the capability to connect with a large number of external systems like Postgres, MySQL, Salesforce. The connectors can be used to bring in the data into event streams. When the events and the data has reached event streams, we have to process them. That's where the event processing part come into play. So event processing provides this capability of transforming and enriching the data before vectorizing the whole chunks, as I said before. So after vectorizing the data, we could store the embeddings into a vector database. So using the data within a vector database, you could retrieve the relevant information or the context and integrate with an LLM to provide a more meaningful response. You could add additional steps like AI agents. That is like, if you want to decompose a query, let's say a user provides a query which is very complex, it can be split up into multiple queries using an LLM model or an AI agent. So this decomposition would provide us with a more relevant information rather than using a single query for it. So it generates a response. We have to validate the response. That is where the compliance and the validation part come into play. And then there is the feedback loop, refinement of the whole process. So the RAG pipeline can be split into 4 core components. One is the data enrichment part. This is the part where we prepare the data. We prepare the data by ingesting real-time events, processing and storing those into vector databases. So the retrieval part is where we get the contextual data from a RAG system using a query that is provided by the user to give a better LLM responses. The workflow orchestration is where we split the query into multiple steps by using AI agents and deliver insightful automated workflows. Post-processing of the whole pipeline is where you filter out the information that is not required for certain uses, governing the data where it doesn't go to people who are not don't have the access to it. So the data enrichment part, let's take the data ingestion and the stream processing part of it. For example, let's say there are multiple sources like POS systems, warehouse systems, and supply system. We ingest the data into IBM event streams using connectors. We ingest into a Kafka system. The ingested data can be used by a stream processing system like Flink that could like transform, filter, aggregate data, and you can move it to a separate Kafka topic or a separate external system to create data products. So the embedding part of it is coming under Flink itself. So the real-time data products, let's say we create textual representation of our data. We kind of chunk and generate embeddings based on that. This could be done from the event processing side, where we combine all the information to create embeddings. So the embedding models can be from watsonx, OpenAI, Claude, whatever the model that you want, or you can host your own AI models. So we store these embeddings into a vector store like Melvis, MongoDB, Postgres, whatever vector store that suits your needs. So this stores the whole embeddings with metadata for fast semantic search. Why do we need metadata? Metadata is required to verify if the data ingested or the provided by the LLM is accurate. So we could store features or metadata alongside with vector store to give more accuracy. So the retrieval and workflow orchestration is where we store the embeddings. So based on the embeddings, we could do a similarity search or semantic search using a RAG system. We retrieve the relevant data, and the relevant data can be provided with LLMs to provide a good response. So you could do everything using event automation by having topics in between all the processes. So the advantage of having topics in between each of the processes is that you have a persistent store of all the responses coming from different parts of the system. So this is the post-processing part. We have real-time insights, we have chatbots, right? So we get the response from LLM with the context. We have to do post-processing. See if the access control or the user has the relevant data. So using IBM event processing, you can apply post-processing rules on event data. For example, before sending a sending a document recommendation to a manager, the system checks for the recommendation aligns with the business rules like minimum order quality, all those things. So we have to do the post processing and the governance part as the last step of our event driven pipeline. On the user's perspective, the inference pipeline would look something like this. The user starts with a prompt asking a chatbot. Let it be a inventory chatbot. Let it be a chatbot that is a medical chatbot or a support agent, whatever it is. So we send the prompt. We store the prompts in Kafka. We pass it to a Flink job. It does a similarity search and gets the context. After getting the context, we will use LLMs to provide a more accurate response. So in the demo, I will be more talking about the application of this using a inventory management system. That's why I have provided 3 different sources like the inventory, orders, and logistics. Okay, coming to the demo. So I would like to explain the overall demo architecture, where we started off with data simulation. We are producing events that could be produced from an inventory management system, like logistics, orders, those kind of things. So we use this data to show you guys how the RAG system could help us in this. So the data would look something like this. So the inventory events is having the event type and the location, all those information like quantity, the timestamp when the event happened, all those things. The order event is having information of the order that is coming from the user. Logistics is the information about whether a product is on its way, where is the location of it, the cost of it, those kind of information. So using this 3 events, we could provide a better response to a inventory management system. So let's say there is a manager who needs to know how many orders are have been placed right now. So by asking a chatbot, it could provide an accurate response like there are 40 orders for Nike AM 270 size 10. So to provide those information, we need to ingest this data into Kafka. So I'm thinking of a system where it starts off with a manager asking what is the current stock of size 10 Nike Air Max in Boston. So the response I'm expecting is an accurate response where the current stock of size 10 Nike Air Max in Boston is 45 units. And the pending orders are 30 units, and there is no restocking recommendation from the chatbot. So the data simulation starts off with generates mock data. As I said, we don't have real-time data available like original data, but we are trying to create a mock data that would put all the information into a different Kafka topics like inventory, orders, and logistics. So this would put every data into different topics. We are splitting all the relevant events into different topics. After ingesting all the data into Kafka, we start off with the processing side. So here we are using Flink processing. Here Flink processing generally applies as IBM event event processing. So I could show you an example of data masking, deduplication, and encoding. So let's say there is an order where we have information of his credit card. We don't want that information to be flowing down the stream of a pipeline. So we have to mask this credit card information. That's where this masking job comes. Deduplication is where, let's say, there is a logistic event where the events are duplicated from the source itself. So we need some way to deduplicate the events. That's where the deduplication job comes in. And we have the last part where the vector encoding, the vectorization of the whole text representation that we have. That can be also done with a Flink job. So event streams, these are the topics that I'm having. I have different topics to store the different events, and there are other topics to store the representations and encodings. So this is the event processing UI. I have split all the processes into different flows so that it's easier to manage, and I could change only a flow. If I have to change something, I don't have to change all the pipelines. I have to change only one flow. So that would makes it easier. So each flow is doing separate jobs. For example, masking a credit card information. So this is a separate flow where it takes the events, masks the credit card information, puts it into a different puts it into a text representation topic or a different topic if you want. So let me show an aggregate example. So we have logistic events coming in. So we would like to know the distinct count based on the status. So as and when the events are coming in, we could get a real-time information on how many events are there based on each category, like each status. There are 3 delayed events. There are 3 in transit events. There are 3 out of delivery events. So this is an aggregate data that gets updated every minute. So we will get the accurate amount. This is an example of masking. As I said earlier, if there is a payment information like the credit card information, you could mask this by writing a stream processor node, and we could like put those information into a separate topic. So you can also write complex pipelines. As I said earlier, we get all the information. We have to do a text representation of the whole data to encode it and push it into a RAG system. So you could do that by in this pipeline. We have 3 nodes in between. First is validating if the inventory items are there. So we don't want events where the whole stock goes down. So let's say there are stocks coming in. If there are orders where we sell out items, right? So we don't want to give the user who is querying the chatbot that there are negative number of orders in the system. So we want to give an accurate system. So we could add validate nodes in between. We could add the duplicate nodes where we remove duplicate events. And then comes the text representation. Text representation is something like we are saying that inventory update for a particular item in the location, and this much unit is there. That can be represented as a text, and then that can be encoded. Similarly, we could do a embedding from the event processing, IBM processor, So this is a node, this is an API node where it calls the Watson X embedding service to encode the whole text data. So if you are still confused what is vectorization, let's say there is a text representation of inventory update for a particular item with this number of units. You would store that in a RAG system or a vector store with the content and the metadata of the content. Then comes the embedding. This is the dimensional vector where the RAG system uses for a similarity search. Another example is an order event where we calculate the amount that might be there for a particular event. We could do a similar thing here. Okay, so how does the vector search happen with a PostgreSQL? So I have used PostgreSQL as my vector DB using PG vector plugin. So I was able to use this DB to store all my context. So what happens is the RAG system queries the vector database. It, uh, it it gets the relevant data. First, it goes to a embedding. I have used a model from Llama, and I just embedded the whole data and stored it into a vector database, which is Postgres. And the search result would be passed back to the RAG service. Okay, so as I said earlier, we have to give more accurate response. So for that we could use a metadata store. I have used Redis. You can use any other key value store or anything else. So for relevant metadata, I have used Redis. So it start off with processing the events, getting the right amount of information and putting it into a Redis system. Okay, so how would the data in Redis be stored? So let's say there is an alert like the product in Boston Nike AM 270 size 10. It has only 45 units that even happen in this interval. So we could store this values into Redis so that we could retrieve this information quickly to verify if our information provided with the LLM is accurate, or you can combine it with the LLM to provide more accurate information. Similarly, you can do that for shipping cost, all those things. Query decomposition. So let's say a user asks a very complex query. What is the current stock of size 10 Nike Air Max in Boston, and why are shipping costs high in Atlanta? So the query one, if you're splitting the whole query, it can be split into multiple subqueries. Here we have split into 2 subqueries. This is done by an agent or a LLM that sits between the RAG or the metadata system. So if you want to split this, we can split it into 2 queries. What is the current stock of a particular product, as well as the shipping cost at a particular location. After splitting the queries, the query one can be used to retrieve information from the vector search or the vector store, like this much of units are there, by doing a similarity search of the latest information and providing a more accurate information. As well as we have the meta data store, which also has a similar information, like there is 45. If there is a difference, we know that there is something wrong with the system, or LLM is hallucinating in between, or there is a problem in the whole pipeline. So we could resolve that by having 2 systems, a metadata and a vector store. So the LLM response combining both of this information would be like the current stock of Syston Nike Air Max is in Boston is 45 units, a pending order is 30 units, and there is no restocking recommendation. Similarly, about this is the subquery to shipping cost query. So you would get the logistic updates from the vector store, as well as the accurate information from the metadata store. Combining these two, you can provide more accurate or refined response, like higher fuel surcharges. Those kind of things can be added. So the RAG service is where the user query, the all the things that I have talked before this slide, right? I have combined it to say it's a RAG service. So if you see here, there is this query decomposer. We split it into multiple subqueries. We use the subqueries to query the vector DB as well as the Redis to get a more accurate real-time response, real-time data. And a response generator, using this data, we generate a response, combine it with LLM to give a response. Then comes the response validator. We have to validate if there is no hallucination further from the model. So this is how it would look like for a RAG system. User queries: do you have enough this much of product? It gets the relevant information vector store. It gets it from Redis cache and provides a LLM response. So as I said, the last step would be the response validator. So the response validator is where our generated data is. There is no difference in the numbers that the LLM provides, as well as the actual amount of product that is there. We can also check if there is hallucination. We can check if a policy is compliant. Those kind of response validation can be done, so that it becomes more trustworthy from the user's perspective. So we validate the numbers, we validate the facts, we validate the policies, and give the final response back. So from the UI perspective, a user would get a response from all these services, RAG services, and all the lookup data, and it goes to the Streamlit UI. You could use an asynchronous pipeline where you send data to a Kafka topic and process it asynchronously. That is also possible, but you can also use a traditional system where you do REST actions and get the response back. So it depends on the size of the model, how much time it requires it to process the process or get the data. So end flow would look something like this, and this is an example, another example of how it would be via the shipping cost high in Atlanta. So we get all the information from different systems. We provide some an accurate response to the user. So what is the benefits, challenges, and best practices? So some of the benefits are: we enhance the AI's accuracy, reduce hallucination by providing relevant, real-time, event-driven data. So we are not making up data; we are providing information based on the actual data that we have. So we improve the compliance and governance, security, all those things. This architecture is scalable. The backbone, the event streams can be scaled up and down easily. It can adapt to any AI solution with real-time inputs. So storing all this information in Kafka or event streams, it would allow us to validate if a particular model is good or not. So let's say there are multiple models. If you want to replay a particular model's response, you could store all this information into a different Kafka topics, replay the whole event to see which model performs better. This enables us to understand which model works better for different applications, as well as there is continuous learning happening within the system. The challenges would be how to ensure a low latency data. So as we have seen, there are multiple systems involved. We have a vector store, we have agents, we have metadata store. So the challenge is to provide data in low latency. Like we don't want people to wait for the response for a long time. That's problem number one. Then the problem number two is kind of related to the first one, where the response speed is less as well as the accuracy goes down. So as and when the response time, if you want to make a response time, we kind of try to make the model smaller, which would reduce the overall accuracy, and it would affect the whole system. So the best practices would be to split up the whole architecture into different microservices, so that we could monitor which system is behaving well. So having a microservice architecture, we could leverage the event streams topics to as an intermediate store between different services. Also, for efficient event processing, you have to split up into different flows, so that it's easier to manage if you're having a small flow rather than having a way too complex one. So as I said, event automation with RAG would give you a real-time AI evolution. So if you need a system where you need more accurate hallucination-free system, you should definitely go with event automation. Please to consider using IBM event automation that enables secure and trustworthy dynamic AI application. I would also like to hear how would you apply a similar system in your industry. So yeah, I would like to take questions if anyone has any.
Okay, well, let's take a look at the chat here. The only question I'm seeing is help documentation URLs for RAG.
I didn't completely understand the question. If you're asking for documentations, I think there is a relevant application there as well. So if there is updates to our documentation, you could use a RAG system to update and provide a real-time data. So if that's you're asking for, if you're asking for a documentation for how to implement RAG, I might have to search the docs for it. I think we don't have any, but yeah, if there's any, we'll definitely provide you with it.
Okay. All right. Anybody have any other questions? Just put it in the chat, and we'll get right to it. All right, Joel. I'm not seeing any. We're a little ahead of time, but we're going to start our next session. Let me look here. At I'm just looking here. Luke, is it at the top of the hour? 5 after? 5 after. Perfect. Okay. So we're going to start our next session at 5 after. And if you'll complete the survey for this session, put that up, and we'll continue on then in 5 after. So thanks everybody for joining, and we will see you in 5 after.